Welcome. What? Hi. Hello. All right. So we might just. Can everybody hear me right? All right. So I'll just project. We'll see what happens. Thanks for coming to this presentation. My name is Freddy. My bias lab portion is on the. If you really want to know more about BSO, written down in the video Devnexus thing. But what I'm more interested about is knowing about you. So the very first question I have is, who's a J2SC developer? Oh, there's some. Okay, Java EE? Android? Alright, so it's a good crowd. We got a mix. And I'm glad that all of you guys show up because memory leaks are real. And we all need to be aware of it. Even though we are in JVM managed language, we're going to walk through some examples today, and we're going to figure out how we can write, new free code and do all this stuff. So, the thing I can bring to you today is that when I was learning about Java, when I was doing what I was doing, I took a lot of shots in the dark, trying to figure out why these things happen. Why is my application, essentially second. Why is my application running out of memory? And essentially, there are very specific steps that will get you very quickly to how to solve your memory leak problem. So today, what we're going to do is we're going to talk about what is a leak. We're going to go talk about why, how GC actually works, and how is that affects the way you write your code. We're going to figure out how to see leaky code, and if you ever have a production problem and you have to find that memory leak, it won't take you days, it will be hours, and people will be amazed. In short, I want everyone today to get a certificate of funding. We're going to fix any leaks that we find, and that's my goal for today. We're going to do it together. We're going to get our certificate from the School of Hard Knocks. So, the first thing we're going to go about, we're going to talk about is essentially preventing leaks. What are the hard leaks? And the second one is GC pressures, carbon correction pressures, and we will go into more detail as those come along. And the second part of our presentation, we're going to go about finding leaks. And we're actually going to fire out our tools. We're going to have some code examples. Depending on the time, we're going to go to 2, maybe we're going to do 3 examples. And then we're just going to walk through, if this were your application, what are we going to do? How do we find it? How do we fix it? So, how do they happen? Who knows this? Oh, you guys, this is the crowd. This is from Geek Fortress. So I'm a geek at heart. I play this game. I can't do it anymore much. And this actually happened yesterday. We were talking on the bar, and I was talking to one of these super fancy C++ guys, and he's like, we're talking where he's a presenter, and he was telling me, why do you think you're talking about memory leaks? It's a JVM. There's no way for you to actually not have a leak. It's all vanished. And I'm like, well, and that's the first problem. Even though the JVM does a lot of stuff for us, we sometimes forget that the JVM is not all same, and it cannot solve a lot of our problems. What memory leak happens is because we unintentionally leave things hanging around. For example, if you have a long-running application and you're adding it to a map, and you never remove it, you keep adding to this map and you keep adding to this map, the garbage collector doesn't know if you really don't need the map or don't need the map keys. So we keep it around. And when that happens, then there's no way for the garbage collector to reclaim it. And that's what the leaks happen. It's not that you're going to get a sec call. It's not that you're going to be like, it's not like you're going to have like a JVM snafu. What happens is you run out of memory. For example, the second time, the most common one is when you register a listener, you want to listen to some events, but then you're done with listening to those events, but you forget to register the listener. So it's blacklisted. And this one comes with a caveat that we're going to go through. that only happens sometimes. That doing this register and listener and not getting to a register creates an actual memory. But the thing is that to actually going down this route, the very first thing is you need to understand how garbage collection works. So what we're going to do is we're first going to go and take a tour of the garbage collection. We usually don't. Most of the time we just let the garbage collectors do their work. And I promise that it's not going to be like a Charlie Hunt where we're going to go down to the bytecode or anything like that. We're just going to do a big overview because knowing how the garbage collector works will make it just a better development. And after we cover how the garbage collector works, then we're going to go in proper and see how the memory leaks that you create or the code that we create interfere with the garbage collector. So that's sort of like the roadmap that we're going to go. And this is essentially object graph, right? We start. So usually what happens is we have what is called a GC root. This is essentially one of the very first objects that says, when this object is created, anything that object refers to, we're gonna keep. So what happens is Duke will go around the JVM garbage collector, and then he starts checking, what can I reach from the GC root? He's saying, okay, I can reach you, I can reach you, I can reach you over there. And if I can do that, that means that these things are being used. I have to keep them around. I cannot dispose of them. Later, because of chance circumstances, you remove one of these essentially connections of any of these references. And then the next time Duke comes around, he goes around and is like, okay, I can reach you, I can reach this other object. Oh, wait a minute. These guys here, I cannot reach anymore from the GC root. So they're then candidates for collection. So this happens, in milliseconds. This happens all the time, and that is sort of like the wow. All right.
Oh, I'm sorry. All right, so let me. Technical difficulties for 60 seconds. Hold on. There's a garbage collection going on. See, it is possible world. All right. Is that good?
Thank you so much.
No problem. All right. So, every time that we have this GC roots, that's how this is essentially the top level how garbage collector works. In the inner work, it gets very, very complex, but in the simple theory, this is what they do. So, what are these GC roots? And in reality, there's probably like 6 or 7 things that the Java virtual machine, and by extension, even like the Android and all those, consider GC roots. But at the most basic level, or at the level that we care about, it's essentially static variables. That sort of makes sense. Live threads that are actually running on the system, and then local variables or parameters. So if you're calling a method and you're passing parameters in, that actually makes it to the stack, and the stack you keep all these parameters going around. All those things, if you pass in an object, those things are considered, GC roots. So once we discover what the GC roots are, we're going to now talk about those little arrows that connect the GC root. And these are called references. So there are 4 types of reference: strong, gravity, weak, and dark. Uh-oh, that's my Jedi physics slide. It's so great. It's like strong reference, gravity. But no, in reality, there is strong, soft, weak, and phantom. Those are the 4 types of reference that we have that a garbage collector has to deal with. Now we're going to go over and we're going to go first with the strong references. These are probably the ones that you know the most. Some of you might exclusively only know this one. And that is when I create my object and I assign it to something else, that is actually a strong reference. The garbage collector says, these guys are tight. Like I know Mike over there, we're tight. Like this is a strong reference right here, right? So same for example here, we are at message, you're adding it to a linked list. Those are things that are all strong references. Now, Here's an interesting question. When we're dealing with strong references, who have seen this construct by way of hands? And you guys, if you're doing a lot of UI work, you probably do this a lot. These are called anonymous, these are called anonymous inner classes. They're anonymous because you don't create an actual name for it. They're inner because you're creating a class inside another class. And what sometimes happens is you get a lot of misinformation on the web about, on the interwebs, about if this is a memory leak or not. Because most of the time when you add an anonymous inner class to an object that you want to listen to, there's no way to remove it, right? It's anonymous, it's inner, it was done there. There's no way for me to almost like remove action listener unless I assign this to a variable and then I can call it up. But then most of the examples, even on the web, don't do that. And here's the question. Who thinks this is a memory leak? Wow. Well, there's one. Who thinks this is not a memory leak? Who thinks that it depends? All right, I gave you a good choice, right? Well, in reality is that, like everything that is hard in life, it really depends. And what happens is, we're going to go with the swing UI because that's close to my heart. What happens is that most of the time, if I'm disposing of this button, I'm not disposing of this button by itself. I'm usually disposing of the button, the frame, all the packages that came with it, right? So what happens is that I disconnect it from the GC root. I usually disconnect not just the button or the anonymous inner class. I disconnect a big object graph. Every time I dispose of a frame, I'm disconnecting the whole thing. So what happens is, if the scope of my inner listener is the same as the graph that is contained in, then there's no memory leak. Meaning, like, if the purpose of my listener is to be with that button until that button gets disposed, and then after that, my listener, I don't care, there's not a memory leak. Now, weak references are, the second type of references. All these are weird, but the weak reference is the one that you actually create, sort of like this construct, weak reference of widget, and then we essentially say new weak reference to the widget, and then sometimes we can do weak widget.get, and that might get us the actual object. Other times it might get us null. And what weak references are essentially a way for you to say, you know what? If anyone else is using this widget object, keep it around and then give it to me when I ask for it. If nobody else but me but other weak references are using the object, then you're free to let it go. So it's interesting because the very first thing, you start hearing about weak references. If it's the first time you hear about weak references, wait a minute, your hair starts spinning. So you're telling me that I can have a structure that's sort of like, if it's not really used, if there's a need for memory, then they can be removed. The first thing that comes to mind is, I can use this for caching. It's almost a natural progression. It's like, I can sort of like use the memory space when nobody's using it. Everything is a weak reference on my cache, and then I can just, if there's memory pressures, because everything is just a weak reference inside my cache, then the garbage collector will start reclaiming some of that stuff. Now, this is Charlie Hunt. And he's a very, very nice person. And we had a conference back in Chicago, a go-to conference. It's not as great as this one, by the way. But he was there, and then there was the question. He said, the only thing that will get me angry if I get a question about using weak references for making caches. And everybody was like, what? So the reason is that you're actually letting the JVM make a wild guess of how to manage your memory. So usually caches have a lot of properties that is not about just when I need memory, get rid of some of my cache entries. Most of the time, when you really think about how you're doing your caches, there are certain things that you want to keep around. Some things you want to do RU cache, at least recently used cache, or least frequently used cache. Or you want to do some type of pruning where you decide what you want to remove. when you let the JVM or the garbage collector make those decisions for you, it almost like, I don't know, it's like you're giving me a bunch of stuff and I have no idea which one is good, which one is fun to discard. So that's why it's always, even though it's the first reaction you get when you learn about weak listeners to use it for caching, don't. Just be there's a lot of caching frameworks out there, and there's a lot of caching policies that you can use. So manage to cache yourself. So the second thing that happens is that when you have weak references, it's sort of trying to solve the problem of the lapsed listener, right? When we saw when you have a listener to something, you added to listen to events on that, and then you decided that you forgot to remove it. And I'm the first one that falls on that. Sometimes I register something that I know has a longer scope, that their scopes are not on the same level, and I sometimes forget to remove it. So a lot of people decided to say, well, what about if we actually create weak listeners? Meaning we use the weak reference trick to say, hey, if we only have weak listeners here, then we're just going to remove the object. There's no reason, there's not going to be a lapsed listener because the garbage collector will be able to collect that because nobody else is using it. And the problem is that when we sat down, and IBM talked about it, made a paper about it, if it was a good idea or not. The thing is that it changes the semantics. Usually when you're doing it, you're implementing, you're adding listeners or removing listeners, that's part of the observer pattern. And you always understand that the observer pattern you have to add and you have to remove, right? So you're changing the semantics. It's almost, you have to add, but if you really don't want to, you don't have to remove it. And this is one of those where the cure is worse than the disease, where, I know if I have a slight cold and then I take one of these NyQuil things, the list of side effects, sometimes side effects may include headache, purple tongue, and then I'm just gonna get the cold. So the thing is when you're trying to implement this kind of things, it's usually you're trying to solve a problem and it looks even more kludgy than if you just subscribe and unsubscribe, register and register, add listener, remove listener. So then the big question is, all right, so the only two big ideas that I had, they're not supposed to be used for that. Then what do you use it for? You use it for what is called canonical maps. And if we ever done database, have you ever wondered that there is sometimes a one-to-one relationship on tables? And you're always wondering, why do I want a one-to-one relationship on that? Can you just throw them on the same thing? Sometimes you use it for saving space, where there's some extra information that this thing doesn't need. That's sort of like what canonical maps are in that sense. Let's say, for example, that many users share an address. Let's say you're doing an application, like a census application, and you have an address, and there's different users that are associated with that address. And that address is not just as simple as 5 lines of code, but it has terabytes of maps about gas lines that go to that address, about structures that are within there, limits and all this other stuff. So the address structure is extremely heavy. Canonical maps allow you to say, well, if there are really no other users that have a reference to that address, then we can get rid of the address. And that is one of the very valid reasons why you want to do this. And it's something that, again, it's not something you want to do every day. It's something that you have to do it when you're thinking about it very, very hard, and you try other things and try to lazily load the addresses or eagerly delete them. And if it doesn't work, then canonical maps might be the solution for you. Oops, sorry. The last thing is, and this is where the difference on the other other types of references is that weak reference can be resurrected. So what this happens is we do have even though we're not as hip at the C++ guy, we do have a finalized block, which is essentially a destructor. We're not supposed to use it. We're not encouraging you to use it because the semantics of when that gets executed is almost left up to the JVM, which means that you don't know if it ever is going to execute your finalized block. But if you have a weak reference, and the finalized block, you have the ability to bring it back to life. So it's I'm weak, I'm about to be garbage collected. And in the finalized block, you get caught, and it's no, you're going to be strong again. You're going to live. And then we got a zombie going around. So that's an artifact. That's what makes it a little bit different than soft and phantom references. Soft references are essentially almost like, it's exactly like weak references, except for the fact that you say, just keep me around until the very, very end. It's almost like, don't garbage collect me if I don't have any strong references. Just keep me around until the end, just for whatever reason. Which is it. So when it's actually you use all the memory, then that's when the soft reference will get garbage collected. But usually weak references will get collected on the next small to medium in the small garbage collections. I mean, usually weak references are eagerly collected. Phantom references are even weirder. They are never there. You create it the same way as you did a weak reference. You say new phantom reference, you pass in the object, and every time you get the object, it returns null. So you're like, okay, that's very useful. The reason why they do that, though, is because the phantom reference have a way to keep track of when it was in queue for deletion on the JVM. So the garbage collector is about to remove it because you had strong reference to that object. You got rid of the strong references. The only thing that's left is the phantom reference. And then it's like, all right, you are good for garbage collection. Then the phantom reference will have the callback saying, hey, we're about to get garbage collected. And they made sure they call them phantom because there's no way to actually resurrect them. It's not like the finalize block on weak references where you can actually make it strong again. So those is essentially your 4 types of references that makes up your GC. Now that you essentially know how top line, you know what your GC roots are, you know what the references, those little arrows that point to things are, most likely you're just going to be using strongs. But this is the second concept that happens, which is GC memory pressure. We call them GC pressures. So what is memory pressure? When you look at memory pressure in terms of the symptoms, they actually look the same as a memory leak. You go into all these tools, these fancy tools that are monitoring how much memory your application is doing or is using, and then suddenly you see sort of like this curve is going up, it's going up. It's almost like you do have a leak. But then the full garbage collection comes and then it disappears. And you're like, what happened there? Why did it really look like this big trend going up? And then at the very end, it just dropped off again. This happens because the way the garbage collector works, and this is the second part. So we know how it works in the very top. Now we're going to go a little bit down and we're going to see what's happening on a generational garbage collector. So usually, Duke shows up, says what's up, and then it starts asking everyone, right? Remember when he was going asking all the different dots, the different objects, are you being strongly referenced, right? So he says, yes, I am. And then he goes on his way, right? Now what happens is this happens every 200 milliseconds. It'll come back again. Some objects start getting tired. This is like the friend who always asks you, like, hey, what are you doing? It's cool, nothing cool, then calls 20 minutes later, hey, what are you doing? Right? So he's still there, it's saying, all right, I'm still being strongly referenced. And guess what happens? Every 200 milliseconds on the clock, he shows up. So then Anna is like, it's like a needy girlfriend, and yes, I am strongly referenced. It's like he's like, you know what? You don't have to check me all the time anymore. Please. So then what happens is he figures that it's a tenure object. So tenure objects are objects that are like, you know what? You sort of have survived. Sort of like 3 queries for me saying, are you still strongly referenced? Are you still strongly referenced? So it's like, all right, you know what? You're tenured. That means that I'm not going to check for you. Instead, it's going to move in what is called to the tenure region, where it's a different space on the garbage collector, and it's going to just stay there, and then nobody's going to check it, and it's going to make your program run more efficiently because those checks are not necessary anymore for this object. So when you're in the tenure space, you don't get checked until there's just pressure for the garbage collector, right? But like all things come to an end. And there's like, I'm sorry, we're not meant to be. And removes the strong reference, right? So now what happened? We just promoted this object to never be checked for garbage collection. It's on a tenure space. But 5 milliseconds later, after that happened, it's like, oh, now you are ready for collection. And he's around with his buddies, hanging around, and probably at a tenure garbage collection bar somewhere, drinking it up. And then, the garbage collector shows up. This happens because, right now, this is almost like the end of the 200 gigs space that you have allocated. He's like, I actually need to eliminate some of you guys. So then, at this point in time, he goes in, he says, any of you are still strongly referenced, because he doesn't know that you guys broke up. So, they're all like, Then the garbage collector will go in and sort of like finalize and terminate them. So this is essentially what GC pressure is about. It's about when you have sort of like this connection, this strong reference to an object, and then because it was being strong for like a long time, but not very long, it was long enough for it to be promoted to like tenure, then it sort of like has to stay over there, and it doesn't have the ability to be garbage collected immediately. Let's see if I get it. All right. And the reason is like, for the people that actually design these garbage collectors, they figure out that most of our things, most of our objects are extremely short-lived. Like, in terms of like 100 milliseconds, 50 milliseconds. And if you think about it, if you look at your code, you got a method, you pass in some variables, you have some intermediate results, you create some objects for doing a little bit of things, and then you're done with it. Then, you discard your intermediate results, you just get the end. Yeah. So it's very lopsided. There's either things that are very, very short-lived, that takes 100 milliseconds, and there's things that are going to live forever, which is, for example, your user object on your database, right? So most of our objects don't survive the eating. Some survive just not like orange, and this is where the GC pressure or memory pressure comes from, right? It's not a leak. It has leak-like symptoms, meaning like every time there's full GC, it's that there's something going on. Full GC is something we try to avoid because it disrupts everything, right? All these full garbage collection means pause the world. It's going to take, whatever it is, depending on the size of your memory. If it's, you have 100 gigs of memory, it's going to take, 30 seconds, and that might be unacceptable for your SLAs and stuff like that. I usually work on the trading industry where, if I have a garbage collection pause of more than 50 milliseconds, everybody's screaming. So we have to deal with this full GCs not happening. So we sort of started getting it. We know exactly like how this. We know the theory. We understand what happens. Somebody was checking in and checking it enough times. I got promoted, and then I let go of the reference, and then it was never collected. But in reality, how would that ever happen? I never seen a case where that actually happens. Actually, I did. And it was a very interesting problem. So, like I said, I work in the financial industry, and one of the things that we have to do is we sort of have to figure out what we think things are valued at, right? So let's say you have Microsoft, or, or Oracle, or Lockheed Martin, all these things trading, right? And then you want to figure out what is the fair value price for that thing, for you to figure out if you want, is it an opportunity to go and get? So one of the things that we do is we sort of like trying to figure out that value is very expensive. Meaning in terms of computer cycles, it's a lot. We don't want to do it all the time. So we create a cache, right? And in this cache, we cache what we call the theoretical value of this trading instruments they are that come in. So the way it works is, we essentially have something from the wire, right? The wires, let's say that we have a market data server, right? Things came off the wire. we sort of like, actually we have a Theo provider. Things came off the wire. They said, now the Theo values for this option or for this company is this ones, right? So whatever it is, 301, 302, 303, right? Then, we keep those in the cache. They're being used in our system. Our system starts querying what is the Theo value for whatever it is, Oracle, and it comes here, it's $1 gazillion, all right? and it's being alive. It's being actually very sustained. These things get promoted to tenure because they're being used all the time. But then a couple hours comes along, right? And now a new set of Theo values came off the wire. So this new set of Theo values are going to be like, all right, these are the new things that we need to price off. So we'll remove the old ones, and we hook up the new ones, right? This happened like 2 hours after, right? So 2 hours after, we send what is called a new fit. And now, if Oracle was worth $1 gazillion, now it's gazillion times 10 on the new Theo values that came in. 20 minutes come by, and new Theo values come, right? And then we do exactly the same thing. But notice what happened was, these guys here survived enough garbage collection to be tenured too. So now we have these two set of guys that were being used very, very frequently, so much that it got promoted to tenure, but we, in the cache, disposed of them because we got a new set of values coming in, right? And like Orange, they are on tenure space. Now, here's an interesting question. Why did we decide to essentially replace the Theo values? Essentially, what do we decide to create a new Theo value object instead of reusing the ones that we had? Anyone has any idea why we decided to do that in the first place? The reason why I decided to do that was thread safety. If you're being on any of these like functional or lambdas or using Scala, you understand that immutability is something that doesn't conduct to thread safety, right? So one of the easiest ways to make your software thread safe is to pass around immutable objects. So the problem with that is, for us, in this particular example, it backfired. Because if you think about it, if you don't mutate your objects, that means that you have to create new objects every time that you need to change the values. And that's exactly what we did. But our objects were already promoted to tenure collections, and we couldn't actually collect them quickly enough, right? Because they were already tenured. So the way to fix this, for example, this particular GC pressure, was that going back in time, we have our cache of Theo values. When new Theo values came in, the way to solve it is we copy the values to our already created Theo values on the cache. So we copy this stuff, and then these guys really just lived a very little time. They were deserialized from the network. We use them to copy the values, and then Duke shows up. But there's no strong reference anymore. After we copy the value, we just copy the value, and then we're done with it. So when other new fit comes in, new Theo values, we do exactly the same thing. We copy the new Theo values to our currently running cache, and then Duke shows up. And then he collects it. So with that, we actually, even though we were doing what is supposed to be your essentially multi-threading 101, don't mutate your values and stuff like that, we discovered that we actually had to, in this particular case, because of the use case that we have, which is these are things that are coming from the wire. We don't know exactly when they're going to come, and we know how our garbage collector is working. We actually have to break the rules and say, no, instead of being immutable, we need to mutate them. But that's that is a way that GC pressure happens in your application. It's somewhat long-lived objects, And then instead of replacing them or updating them, you essentially replace them, and then now they're just in tenure land. Last one is starvation. So again, starvation is, usually you read this as in like threads, but what happens is that sometimes this is not a hard leak again. This is not like you're holding a strong references that cannot be garbage collected. But you run out of memory, and you're trying to figure out, you look at your code, and the code looks fine, and it's like, what's going on? Why am I running out of memory again? And the reason is starvation can be a problem when you have producer and consumer queues. So what that means is if you have a queue where you're throwing stuff in, and somebody else from the other side have to like consume them, then you have the risk, if these are not balanced correctly, you have the problem of running into this out-of-memory exceptions, because essentially, the consumers cannot keep up with the producers. So, they drop, the way it's supposed to work is, a producer puts something on a queue, a consumer goes, gets it, and it's balanced this way, right? But when consumers go wrong, then what happens is the producer keeps adding stuff. This was me yesterday when I was at the leaders' dinners. And the consumer is nowhere to be found. And the producers just keep adding things to this unbounded queue. And because the consumers cannot consume fast enough, then you sort of have like all these things on the queue that I keep growing bigger and bigger that are being strongly referenced. The garbage collector says, I cannot eliminate any of this. And you're having starvation problems. And that's one of the things that, you're trying to like fit all these things, they don't fit anymore. And the biggest reason that happens is because you have what is called unbounded queues. And it's one of those things that when you first think about like things, it's like, oh, I have to create a queue, right? I wanted it to be unbounded because I don't want to drop anything, right? But when you really think hard about it, having an unbounded queue can cause problems, right? You really don't have to have an unbounded queue. You can have sort of like a somewhat large, but a medium size, something that you don't expect to go more. And you can have blocking queues. Blocking queues are the ones that you bound to them, like you bound them, you give them a size, and then you say, you know what, if you're trying to insert and there's no space, then I want you to wait a little bit, right? Until there's space for you to go in, and then you go in. So that at least that way you can balance out, producers and consumers. The consumers will have a chance to catch up and not give you that big memory leak that, from having unbounded queues. So let's go about finding leaks. So we're getting into the second part of the presentation, when we're probably going to go through some code. And then we're going to try to, all of us together, we're going to try to find all the memory leaks using the knowledge that we have of what things could be happening here. So the very first thing is, every good plumber has good tools. So the tool that we're going to be using, there's two of them that are free, and just going free. I mean, I bet everybody here has their tool of preference, but if you don't, at least you have the access to these two. JMap, which is essentially a command line utility that allows you to essentially, you specify JVM, it allows you to get a dump of what's going on inside there. The other one, Visual VM, which is essentially comes now bundled with the Oracle JDK. So if you download the Oracle JDK, if you go to like bin folder, there's a JVisual VM, you can start that up and you can use that. And this is the guide that we're going to use just because it makes it so easy just to spot these things. Now, the one thing you have to understand is if you have to troubleshoot a memory leak issue, the larger the leak, the easier it is to find. So what that means is, like, for example, if you have only like 1 gig of memory, right? Then, and you're trying to find something that is using 500 megs of memory, you're going to find it. But if you have 1 gig of memory and you're trying to find a 20K memory leak, like something is, I think is growing by 20K, it's going to be very, very hard. So what you want to do is you want to collect a heap dump where you have a problem, right? If it's very small, if it's noise against the garbage collector, chances are you're not going to find anything wrong. If it's something like, oh gosh, I'm using 90% of my memory, you will find it. I guarantee you, you will find your leak. Now, the way to do it is you have to collect a heap dump. And this is where, like, you know, this is the reason why our marketing department thinks we're weird. It's because this is what a natural conversation that happened. So, and we have no idea she was essentially overhearing us. We're sorry. I mean, that's the only thing I had to say to her. But it was a real conversation. This is what happens. But yeah, you want to get a heap dump. And then when you do a heap dump, then you can essentially go and traverse. What are the strong references? You know, I know like usually there's weak phantoms and all that. You're probably dealing with strong references. So what are the strong references? And then you can see the object sizes that that are you know, where the leak is happening. So who wants to go palming? All right. So let's see. Just give me 1 minute. Can you guys see the code fine? All right. Let me see first if I can run it, and then after running it, we can at least. Yes, reload classes now. Oh no, that was another one. Hold on. Sorry. And where are you? No, not here. Hold on. Okay, hold on. Let me just do this. Oh, no, not you. Sorry. Got too excited. Finally. So this is my new app. It's essentially going to be an laugh out loud cat search. Right? So I create this great app. You know, I'm going to do it offline just because I don't trust my phone internet. And what it does is it searches, it picks us up some LOL cat random things, right? So this is great. You can go and browse them all. You know, it has a neat feature where you can actually click on one of the images and it pops it up. And so it's a great application. I think it's going to be, Facebook is going to acquire me very soon. So actually, I do feel like that some days. It is really binary. Either you know exactly what's going on, or you're like, well, I don't know. We'll figure out where we are in today, right? So great thing, right? So you know, I can actually have a little button that allows me to close all of the windows that I open. You know, because let's say I want to click on this one. You know, or if I want to click on this other guy over here. You guys know what that one is? It's called Yoda conditions. And it's because if you read it, it looks like you're speaking Yoda. It's 5 equals count. The first, do or do not. So I had this big button close. Oh, it closes all my stuff. It's like it's the winner application. Now, let's see what happens when I fire Visual VM. You know, I've been getting some reports from the field that is this application has been crashing their machine. We're going to try to figure out what's going on. You know, and then we suspect there is a memory leak, right? So we go in. We connect. And then this is Visual VM. I'm going to try to close these 3 windows here just so you can get it. So when you're dealing with a memory leak, this is the one thing that you want to look at, right? You know, you're running your profile, your application locally or even remotely. Visual VM can actually execute remotely using RMX and JMX. So this is what you're looking at. You're trying to figure out, am I running into memory leak, right? You know, there's a way to force garbage collections on Visual VM. It will respect your code, meaning that if in your code you say, I want to explicitly avoid garbage collections, like there's a way to disable external requests for garbage collections, this will not work. But for all intents and purposes, for this presentation, that we can actually do that. So every time I click perform GC, I'm performing a full garbage collection. So things seems to be fine. Let me open a couple more windows now. I open this window, this window, this window, this window. Windows 8, I hate you. Oh, there it is. Okay. Okay, we got to submit a bug report about Windows 8. I'm sorry. Hold on. All right. So we open a bunch of stuff, right? And then I'm gonna close them all. And no, that one I did on purpose. There it is. Now I go perform a garbage collection. I noticed something, right? I perform a garbage collection, and my memory profile is still going up. So there's something going on. Now, now that we know there's a potential memory leak, let's first look at the code, and then let's see first if we figure out what's going on, right? The code it's that simple. This is essentially the main things. There's your search button, right? All these are just essentially they're bound components. I get a bunch of URLs. An image view is a component that displays the URLs. What I'm saying is I want to view that URL. I wanted to add it to my image flow pane, which is that little thing over there. And then the other thing I'm doing is that if you happen to click on the image, there's a event handler right there. Remember when we talk about like doing listeners and anonymous listeners? There's one in there. So I'm saying when I click it, because I know when you click it, you love it so much, I want to open 20 windows, right? So from I equals to 0 to 20. And the reason I had to do that is because I was doing this first at home. And you can see the memory leak if you open one window. But it will be like probably until the next 2 presentations over. So I needed to speed things up. Now let's look at the create frame method, right? The create frame, very easy. We create essentially a new stage where we are going to put the new image, the image that you clicked in. Oh, very simple. And the last thing I'm doing is I'm saying, because remember that close button, the one that I can click that closes all the open windows? I need to keep track of that, right? So what I do is I go into current pop-ups, add, so I know that these pop-ups are going around, and I can iterate through them and close them when they actually ask me to close from the main window, right? So far, so good. As far as I know, there was no memory leak. No, I didn't see any particular bad code I did. I sort of knew that I'm doing an anonymous inner class for the listener, but this only survives as long as my main application. And then if I remove the main application, that goes away. So I'm not exactly sure what it is. Now, this is where we go to Visual VM. We obviously know there's a leak. And the very first thing you want to see, like what we talked about, is you get a heap dump. Don't laugh. This is serious. It took a while. When I first started doing this, it took a while. But we got essentially this is a heap dump of my running application. I'm going to go to classes, and classes is going to tell me essentially how many objects, how many instances of these things you have running. And instances is one measure. The other one is essentially how much memory are those instances using. If you're having a memory leak, chances are that the first thing you want to do is essentially you want to sort by size, because essentially that's how many bytes the object is using in memory. Sometimes the number of instances is not as bad, or it really doesn't matter. You can have 1,000,000 strings, and if they're all one characters, who cares? This is the guy that you're looking for. You're trying to see what kind of my objects are using space. So we can see there's one that really is huge, right? 65 megs. That's using most of my application. So once you find sort of like, and this is one of the things that every time you're trying to do you're trying to troubleshoot a memory leak, is you have to get past that everything looks weird, but everything looks weird is when you look at my code or the code that I created, it doesn't look like I am doing any byte arrays, right? There was no byte arrays in there. I didn't create 67 million of these things. But what happens is usually the memory leaks are subtle things that what you only get to see is sort of like the surface. You get to see the end result. This is what is actually using all the memory. So how do you get from, OK, I know the byte array is sort of like the culprit, but I don't know exactly how that relates to my code. The way you do that is you sort of right-click. No, but I'm getting the hang of it. I'm getting the hang of it. I know how to get out. Oh, gosh. OK, I lost it. Sorry. Show an instances view. I'm going to learn how to just use the keyboard now. So the very first thing I said is, show me the instances, right? So what we had is essentially at the very beginning was a summary saying there's 100,000 instances. They're using 68 million bytes. Now I'd right-click and say show an instance view, and what that's telling me is, all right, let's look at those instances to see what's going on with them, right? And you can see that they are almost the same size. A lot of them are the same size. Anyone has any idea what these are? Let's see. Images. Yes. So these are actually images, and you can actually see it. If you go in, there's all of them look to have almost the same size, or at least they're consistent on the same size. And you're like, OK, so I'm holding on to images, and you're trying to figure out, all right, what images am I holding on? So the next step is you right-click, and then there's this command, show nearest GC root. And this is the command that essentially translates that out-of-the-world thing that you have no idea where it was created to where your code is. And then we can start seeing things, right? So what do we get to see? We get to see, let's see if we can open this a little bit more. So we can see that current pop-ups, that was the map that I'm using, it's essentially the controller is the one who's holding everything. But I can see that the very first thing the controller is holding is my current pop-ups map. And then I'm like, yeah, the map that I used to actually close things. Then I go back to see it. And this is where it always happens this way. It's so much evident once you start seeing this. It's like, did I ever clear that map? And then you go back to the code, and you're like, all right, what happens when I have to when I click on the close all button, right? And then you're here, and then you go. And then you're going at fancy Java 8. That's thanks to Jim Weaver. It's over there. Lambdas. And I realize that I'm looping through the current pop-ups, right? And then I'm closing every frame. But I never actually, even though the frames are closed, and theoretically they're supposed to be disposed, I'm still holding a reference in there. Oops. Sorry. I'm still holding it. Wow. Must have had it in the wrong place. I'm still holding a reference to them in here, because I never clear it. So how about this? How about if I go, and after going through all of them, I do current popups dot clear, right? Then let's see, the just-in-time compilation. I wonder if this is going to work. If not, we're just going to restart it. Actually, let's go build, make project. I wonder if I actually did it. No, it didn't prompt me for that it actually reloaded this stuff. So we're going to see. We're going to try. No, oh, I see. I actually closed it. Right. So let's run it again. And it's not main panel. Yeah, it is main panel. All right. Oh, and then we're going to just kill this guy. So now we're going to try to do the same thing. We're going to open a bunch of stuff, and we're going to see if our memory leak went away. Right. Where is my LOL cat thingy? Oh, just give me 1 second. to window project. There it is. So main panels. Yeah. So debug. All right. We do have hold music. That's awesome. All right. So now it's our application running. It's searching offline. I'm going to connect now to Visual VM real quick. There it is, main panel. And then we're going to monitor it, right? So we got our memory there. I'm going to do a bunch of clicks, right? Click, 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 click. Right? Ooh, big memory profile if you saw under there. You know, I garbage collected it. And I expect this because the windows are being used, right? So there's nothing there to garbage collect. But, ooh, at least it's on the top. If I click this guy, it removes everything, right? Now, these guys are in tenure already. So that's why, like, even though I remove it, they're still there. I'm going to perform a garbage collection now. What do you think is going to happen? And victory! We are heroes, right? But the idea is sort of like, this is sort of like the process you go through, you know. You don't have to be afraid. Things look a little weird. But if you just follow the steps that I said, you know, find the biggest thing, go to see the instances, find your nearest GC root, you start seeing that in that path, there is something that you will identify that's yours, and you're like, okay, I sort of understand what's going on. How much time do we have? Oh, do you guys want to do another one? Or do you want to open for questions? Who wants to do another one? Who wants questions? Nobody wants questions, right? Good. All right. All right, so this was my first, LOL cat servers. Facebook called me up the next morning saying, we love it. After you fix that memory leak, we're great. We always about doing things and breaking things. So, so they asked me, now we want you to create an LOL cat server. So the way it's going to work is we're going to have all this server running, and all these clients are going to connect. And when they connect, they're going to be served an LOL cat image, right? So let's look at the code first, because that one is mostly code, just because there's no interface, but it should make sense. So I'm doing it in, and this is where the difference is. Instead of me doing it microservices or being very fancy, I'm actually doing it by hand. And just creating an actual socket and doing things. And that's just the way I like doing things. Well, not I like, it's just the way the environment I work likes doing things. So this is my LOL cat server. The way it's going to work is we're going to essentially create a socket, a server socket. We're going to set connections on a certain port. As we accept connections on the port, we're going to add it to our connections map, right? So, your application connects to me. I add it to the connection map, and then at a particular rate, I'm going to go through the connections, and then I am essentially going to send you an LOL message. Now, have you guys used byte.rate output streams? Yes? All right. So for those who haven't, what it is essentially, this is one of the ways, like in inline piping, you can actually like serialize objects. The way it works is you create a sort of like a byte.rate output stream or an output stream, object output stream, and then you put in your code in your object in there, right? The output stream there will then code it, and then I sort of collected it into like a byte.rate output stream to actually send over the wire. So very simple stuff in terms of stuff. I encoded my image. I create a new LOL message. I put in the bytes that I require for my image. And then I call connection send message, right? Now, in send message is very simple. I'm using an object output stream. Now, who has used object output stream? That one I suspect more people have used it. If you have not used object output stream, that is the actual one that byte array output stream just is essentially a container collector for arrays. Object output stream is the one that actually gets an object and produces a bunch of bytes that you can use for doing whatever, right? In this particular case, the object output stream is connected to the socket, and then we're sending all these bytes through the socket. So let's see if I can start. So that's my server. And then let's go real quick. We're going to take a real quick look at the client. Client receiver is much easier. The only thing it does is it creates an image view. And then it connects to the socket. Then essentially the client receiver then creates an object input stream. And then when it starts, it just goes into a loop and says, whenever we have a message that we can read, we read it off the wire, we reconstruct their image, and we put it out in our in our frame to display. So let's see how that looks like. So we're first going to start debug server. Okay, so the server is running. Debug client. The client connects. Now, yes, it's a very fast server. If not, it will have taken me years to reproduce the actual memory leak. So I'm just going to leave it minimized. But the server and the client are working right now. So the server is sending stuff. The client is consuming it. And Max Zuckerberg calls, say, I think you have a memory leak. So I'm going there now, and then going to LOL cat server, right? And then I'm taking a look at the monitor, and then let's see, it sort of looks like there might be a memory leak. You're not sure. You let it run for a little bit more, and let's see what happens. Let's see. I'm going to perform a garbage collection, right? Just wanted to be sure. It's still fine, right? Of course, that happens all the time, by the way. It's like they say, we suspect a memory leak. You look at it for like 2 minutes. It's like press the garbage collector button or you make a garbage collection, it looks fine. It always happens, 20 minutes after you're into it. That's when actually it shows his real head, what's going on. Now, let's see. I'm going to do another garbage collection and see what happens. Now, notice something. It collected, right? But between this point and this point, it didn't go all the way back down. And if you have an application and that you say, I'm really not keeping any information around, I should not be producing, even like this is a small difference, I should not be producing that much, anything that is, it should be no difference. It should be like, there's nothing in there. Aside from my static objects and the stuff that I'm looping through, there should have been anything being created. So then you start suspecting, so you let it run a little bit more. We try to do a GC again. And now you know for sure there's a leak. Because, you keep seeing this pattern. It just keeps going up. And if I keep this running, I know I'm going to run out of memory on my computer. Now, who even has a suspicion of where it is? Oh, if you were so sure, you probably already know. But let's see it. What was that? Your connections? Oh, my connections are not closed? That's true. So that even though actually that's true. That's a new leak that we're not seeing here. But he's right. I never disposing of the connections. But in this particular case, we only have one connection, one client and one server. So it's not that I am creating a lot of connections. So the leak is related to something else. Oh, you see, it reassign more memory. Let's see if we can say. Anyone else have any idea? You can be wrong, it's fine.
Every time you're creating an image and you're not cleaning that image, you're sending a message, I guess, LOL message.
Mm-hmm.
Then you're not cleaning up. Every time you're creating new one.
So every time I create a new image, I'm not cleaning it up, meaning like disposing of it? All right, hold on. I think it's could be a little bit there. I am not keeping the image for so long. when I do a garbage collection, it's supposed to take it because I have no references to it, even though I explicitly didn't say don't use it. But yeah, we'll come back to that one. So you said something about
If you're not clearing the stream after keeping the streams open rather than starting and stopping.
the streams open. That's okay. So that's getting a little bit closer. And then somebody else.
I was thinking maybe the thing was consuming slightly slower than you were sending out stuff.
Oh, so you're saying like almost like the producer-consumer problem where I'm sending things faster than it can be pulled out the wire. That's a good one to keep in mind, but most of the I/O operations versus CPU operations are like orders of magnitude. So me sending this stuff is very, very slow for the CPU for it to pick it up. So while that could happen, and it's not particular in this case. So what I'll do is just in the very good suggestions, very great, but at the end of the day, we're like, we don't know. So let's go and take a heap dump. Now, we're going to do exactly the same trick, right? We go to classes, we quick concise. Unsurprisingly, we're dealing with images, right? There's a byte array in there somehow, so we're like, am I really disposing of these guys and I'm keeping them around? So showing instances view, just like we learned, and we can see that there is a bunch of them that are the same size, so we know that it's related to that. Show nearest GC root, right? Now, let's see what that tells us. Wow, this is weird, right? It's holding to the OOS variable. That is our object output stream, right? So we're like, I don't get it, right? This is something that I'm writing to the object output stream. I'm not exactly sure what's going on. And this is something that a lot of people, it definitely got me the very first time. When you see something that is like, it doesn't make too much sense to you. Like it's not like I'm holding up to like a map or a collection that I'm not clearing up. In this particular case, all that stuff is getting stuck on the object output stream. But I'm sending it and they're being consumed on the other side. I'm not exactly sure what's going on. And that's when you go to Google and then you do object output stream memory leak. And then you sort of start reading about it, and then suddenly you find something called write on shared. And that should start giving you a clue. What's going on? And then you start reading about it, mark as reset. So what's going on? The reality is, object output streams are very, very efficient at a couple of things. When you send stuff through the object output stream, and the object output stream is long-lived, what happens is it tries to cache what you're sending. So if I send one image, it says, oh, okay, you're sending that image over. I'm going to send it over, and I'm going to keep sort of like a reference count. I'm going to keep a reference to that image just in case you send it again. And then what happens is if you send that image again, then the object output stream will be like, wait a minute, I don't have to send this image again. I know that you send it, but I'm just going to tell the other guy over there, just remember that object that I sent you like 20 minutes ago, pretend that I send you again. So instead of sending the whole object, it sends essentially an ID, a hash number that identifies on the other side, what object to pull out, and then sort of say, hey, this is a new object. So that way, it's very efficient. If you're having a network connection, you don't have to send those images over and over again. You can just say 1, 2, 3, right? Now, I did a little trick in the sense that in my program, I'm not sending the same image. I'm always creating a new message object, right? So the object output stream is like, he doesn't know better. The object output stream thinks like, okay, this is a new message object. You might send it now, you might send it later, and I'm going to cache it. So it caches it and then sends it out again, right? It caches a new one, And then when you think about it, for my application, I don't need it to cache it. I don't care about caching because my messages are going to be always new. I'm never going to resend them again, and I get rid of them after I'm done. So in this particular case, the right solution is to say, and there's like many ways to do it, but I'm just going to do it the easy way. After writing the object, I'm going to do reset, which essentially says to the object output stream, forget all the stuff that you did. Like all that caching that you're doing, just reset it. We're going to reset it from now. And what happens is the object output stream will send the same reset. It will send it to the consumers, and the consumers will get it. It's like, OK, fine, I'm going to forget everything about it, too. So let's see if we can JIT this stuff. And let's see if we can load it. Yes, I want to reload these guys. Class is reloaded. Now let's see how Visual VM is looking on the monitor. Whew, that's a memory leak, right? Now my new code is loaded. So now it's resetting. I wonder what happens if I do a garbage collection. Victory! Oh gosh, that was a good one too, right? All right, so we got 5 more minutes. So what I'm going to do is we're going to give it, oh, Lord. All right, so we're going to, we're just going to go to the conclusions. So what makes memory leaks happen? Big thing is strong references. Thread starvation, we didn't get to do that one today. We can probably talk about it a little bit more. But what it means is that producer-consumer problem. Oh, sorry, I have it twice. Sorry about that. And GC pressure, right? When things get, usually when something gets promoted to tenure and you didn't intended it to be, that's called premature promotion. So, and there's some ways you can deal with it. Some of it is like GC tuning and all that stuff. But other ways is just understanding what's happening behind the scenes like we did today, and then saying, oh, I can just change my code a little bit and this goes away. In terms of the tool, Visual VM will help you out. It's free. It's always there. And remember, you now know how to get the heap dumps. And essentially, you can navigate to where it tells you where the things are. So that's the biggest thing. And you guys just got a certificate of plumbing. We are great plumbers from the School of Hard Knocks. If you want to hear more about this, Java Pop House, that's my podcast. We talk a lot about these things and more things and fun things. That's my email if you want to send any questions you have about it. This actually is on GitHub, all this code, if you want to play with it at home. And that's it. Thank you.